Hi, everybody. You might hear some heavy machinery sounds in the background during all this. People next door to me are getting their lot leveled so they can have a lawn. So, yay. If you hear it, you hear it. Hopefully, it won't be too big a distraction. So, today we're picking up on the notes with electric current. Let me shrink that down a little bit so I can grab this and show you where we're at. Right up here. Top of these notes. Okay, go bye-bye. And let's begin. Electric current is defined as when charges are not static. So last time I taught you something, which was yesterday, if you're keeping up like you're supposed to be. We talked about static charges. Charges building up in one spot and not moving. They can jump, but they're not going to flow. This is flow of electric charge in one direction. Oh my god, which one do we write down? Whichever one you want. Both. Neither. It's your life. Right, you can pause now and write down the one you want, if not both, but I'm going to move on. Electric current is measured in this unit called amperes, capital A for the abbreviation because it's named after a dead person. And we measure it with a device called an ammeter, though nowadays there's this thing called a multimeter, which is much easier to get your hands on. And it combines an ammeter and two other meters I'm going to tell you about today into one device. You just got to flip a switch or turn a dial to get to the right setting. If you know anything about electrical work, you know what I'm talking about. If not, ask your parents. Alrighty, what causes charges to flow? A potential difference, also known as a voltage difference. Alright, we measure this potential difference in volts with something called a voltmeter. So this is the only time in physical science class where the unit name and the name of the thing it's measuring is about the same. Voltage measured in volts. The abbreviations are the same too. Capital V for voltage difference, capital V for the unit volts. And the unit's capitalized is named after a dead guy. The dead guy's name was Volta. I think he was Russian. I don't know. Anywho, what is voltage difference? So imagine, if you will, you have a water pump pumping water up to a water tower. Have you seen the water towers around Wayne County where your water comes from? One pump pumps all the water up there. That water is high above the Earth's surface. It has a gravitational potential difference. The difference between where it is and where it wants to be on the ground. Okay, so that gravitational potential difference is the energy that pushes the water from the water tower through the pipes into your house. You don't have to have a pump pumping water into your house. One pump pumps water up into the tower, and that gives the energy for the water to get to all the houses attached to that water tower. Alright, electricity works the same way. We put electrons somewhere they don't want to be, like the negative end of a battery, and they want to go back on their own. There's a potential difference between where they are and where they want to be. Give them a path, they'll flow. Alright, voltage works the same way as a toothpaste tube. So basically, the voltage difference is just putting pressure on the electrons that are already in the wires in your house. The wires out on the street, above the street hopefully. Some neighborhoods have the electrical wires buried in the ground, but whatever, you know what I mean. Right, so those wires already have electrons in them because everything has electrons in it. What the power company does is just puts some push to those electrons. They put an oomph on it. It makes those electrons move through the wires in your house to the outlets. Plug something in, electrons move through the cord to whatever you plugged in. Alright? But if you squeeze one end of a toothpaste tube, the toothpaste comes out the other end, right? How far does the toothpaste actually move in the tube? Maybe about that far. Not very far at all. So if I put pressure on one end of the toothpaste tube, the toothpaste coming out the other end is a toothpaste that was already down there. I'm not squeezing so hard that a molecule of toothpaste goes out the end. The electrons in your wire are also moving very slowly. They're all moving at the same time, but they're moving slowly. In fact, it takes an electron 1 hour to move 1 meter. You can't see on the camera. A meter, you know what a meter is, roughly a little over 3 feet. through a wire. So they don't move very fast, but they're all moving. That pressure put on them, like the pressure in the toothpaste tube, is through the entire wire. I hope that makes sense. If I could draw it for you, it'd be easier, but whatever. Alright, electricity flows in a circuit, which we all know is a closed path that electric current follows. Kind of like a pipe through which water is being forced. If I break open the pipe, the water doesn't go where I want it to go anymore. If you break open the circuit, a switch that opens, or just cut the wire, electricity no longer flows through the wire. There's your pipe analogy. Alright. How we make electric currents. One of the ways we do it is with batteries. I mean, technically they're not batteries. They're just called that. And if you ask nicely in the comments section, I might tell you that story. But not for now. Two types of batteries we know about are wet cells and dry cells. So the first one is a wet cell. This is the first kind of battery invented. You got two metal plates connected to two terminals. There is a drawing right there. My beautiful artwork. And there'll be a picture coming up in a little bit. The metal plates are sitting in an acid solution. That's what makes it a wet cell. If you've ever dealt with a car battery, you pick it up, you feel something sloshing around inside. That's the sulfuric acid. There's a reason those things are sealed up tight. Okay, so reactions between the acid and the metals create a voltage difference between the two plates. Alright, so there's a bunch of little blanks for you to fill in right here to explain how that voltage difference is made. We're going to go there now. How the wet cell works. The acid steals electrons from the copper. That's why when I drew the copper, I put a bunch of little plus signs in it. The acid pushes, supposed to say pushes, not pushed, whatever, electrons into the zinc. That's why the zinc is all negative. So now I have a potential voltage difference. I got electrons bunched up in one spot. They don't like each other, so they repel each other away. They love the positive charges on the copper, so they're attracted to the copper. They can't travel through the acid because the acids then keep them separated in the first place. So I gotta give an external circuit, a path outside the battery, to go. And in your drawing there on the notes, that path goes through a light bulb. Electrons want to go back to the copper through the wire. So the word copper should be bolded there, not wire. Sorry, I goofed. It happens. For those of you that already put the word wire in the blank, pay attention. Ugh. Alright. And there's another drawing. Copper rod, zinc rod, attached to, this is something called a voltmeter. And you'll get the needle going over. Copper electrons are stolen from there and pushed into the zinc, and it goes out there and back through the red. There you go. That's a wet cell. The other kind of battery is a dry cell. Instead of an acid solution, it has an acidy paste on the inside. I'm sure some of you have opened up a battery before. One of the round ones, a D cell, a AAA, whatever. And you've seen the pasty stuff on the inside. If it was old, it could have hardened up and dried up. But if it's a little more fresh, it'll be like a paste. Don't use it as toothpaste. That'll be a dumb idea. Don't do that. Okay, so that's why it's called a dry cell. It's not like perfectly dry, but it's not sloshing liquid either. It's drier than a wet cell. And here's a cartoony picture of it. Also have a cartoony picture on your notes. You have the inner zinc casing, the acidy paste, the cathode, which is a graphite rod. Graphite is carbon. And let's talk about how these things work. Acid takes electrons from the carbon rod, which is in the center. That's why on the drawing I gave you, the carbon rod is positive. Shrink and go away. There we go. Acid puts electrons into the zinc casing around the outside, and they want to go back to the carbon rod. They can't go back through the acid paste. You have to give them an external circuit, a path, a wire attached to something that uses electric currents. Okay, there we go. Wet cell done, dry cell done. The next thing is resistance. So we've had current, we've had voltage difference, and now we have the third thing that affects the flow of electrons, resistance. Tendency of a substance to oppose the flow of electric currents, converting electrical energy into thermal energy and light. Got it written down? If not, pause because I'm going on. Resistance is measured in ohms and measured with an ohm meter. Again, ohm meter, voltmeter, and ammeter, all just in one thing called a multimeter. Okay. Sounds like they're coming through that wall right there, but they're not. At least I hope not. Jeez. Resistance of a wire increases if, okay, so at the bottom of that page of notes, right here, 3 things affect the resistance of a wire: temperature, hotter, colder, thickness, thinner, thicker, length, longer, shorter. We're talking about temperature first. Okay, so temperature affects resistance by making it harder for electrons to flow if the wire is hotter. You can read that and write it down while I'm talking. I'm going to give you an analogy. It's like one of the hallways at the school. All right, if a bunch of people are just standing there in the hallway, you could probably weave your way through them relatively easily. You couldn't go in a straight line. You'd have to, juke and jive, whatever, but you can get through it. That represents a cold wire, with the atoms or the molecules being the people not moving very much. Hotter wires, anything that's hotter, you know that the molecules are shaking more, moving around. So imagine those people that were just standing there in the hallway now decide it's time for a mosh pit. Google mosh pit if you don't know what it is. They're flailing about, they're kicking, they're punching, they're whatever, and you got to get through it from one end of the hallway to the other. Yes, you can do it, but it's going to take you more time because you're going to bounce off of people. So a hotter wire is going to make it harder for an electron to go through it because all the atoms, molecules are bouncing around. Well, yeah, bouncing around, shaking more in place, and bouncing around the electron. So what do you write down? Hotter, more resistance. Colder, less resistance. Alrighty. Resistance of a wire increases if the wire is thinner. Why? Okay. Remember what the school looked like? There's this one hallway, I call it the 8th grade hall, I think it's called the B2 hallway. It still smells slightly of pee from when the 8th grade boys used to be in there and just peeing all over the bathroom. Yes, you did when you were 8th grade too, don't deny it. But anyways, so that little hallway over there just off of ISS, it's about this wide. And there's lockers, so it gets this wide when the doors are open on the lockers. And you gotta get through it. Is that easier to go through, or is the E building hallway in front of my classroom easier to go through? Well, obviously the E building one's easier to go through. No matter how much people are moving around, it'll still be easier to get around them if there's more space for you to go sideways. So thicker wires, because they have more room to move around, have less resistance to the flow of electricity. Thinner wires, because there's less room to move around, have more resistance to the flow of electricity. Thinner more, thicker less. Thinner more, thicker less. And the last one is length. Longer wires have more resistance. Shorter wires have less resistance. The reason for that is the longer wire has more atoms for electrons to bump into, slowing them down. Alright. Okay, so that's done. Now we need to go to the other sheet. No, we don't. Little thing for your personal edification. How light bulbs work. I'm not talking about the spaghetti ones. I'm talking about the normal light bulbs, the ones that have the filament inside of them, the ones that can actually break and burn out. When they do, you get a loud popping noise out of it. Alright, let's see, is that better? Oh, I can see much better now. Okay. So, light bulbs, like the ones invented by Thomas Edison and his crew, have a filament, which is a very thin, very long wire of tungsten. Thinner than a hair, 3 meters long. Then they coil it up till it's this long. So it's coiled. And they put it inside the light bulb. So though it's made out of tungsten, which is a good conductor of electricity, it's thin and long, so it has high resistance. If you recall from earlier on in this PowerPoint, resistance changes electrical currents into heat and light. That's what light bulbs do. They glow and they get hot. So there you go. That in there is 3 meters of filament, thin tungsten wire, coiled up until it's only, what, an inch long? So wrap around. Put between the positive and the negative. I don't know which one's positive and negative, I'm guessing. And electricity flows through it, lighting it up. Alright, now on the second page of notes. Currents, voltage difference, and resistance are all related by Ohm's law. So, 3 blanks you fill in, Ohm's law tells us how blank, blank, and blank are all related. Currents, voltage difference, and resistance. If you want to write down the units, go ahead, but I've assumed you've memorized all of your units by now. Anyways. The current in a circuit is equal to the voltage difference divided by the resistance. Ooh, that's math. That's current equals voltage difference divided by resistance. All I gotta do is put all the proper little symbols in there. And it's I equals V over R. Capital I. That's not an L, it's a capital I. Remember, if you will, when we were in the classroom, we talked about the atom chlorine and its symbol Cl. The capital L, the lowercase l and the capital I on a lot of these fonts are the same, including this font here. Sorry. So the capital I represents the current, measured in amperes. Voltage is the voltage difference, measured in volts, VVV. And the resistance is, for the capital R, measured in ohms. And the symbol for ohms is the Greek letter omega, capitalized. I don't know what lowercase omega looks like. Sorry, I'm not Greek. Okay, got all that written down. That's I equals V over R. So this is on the, where'd my mouse go? There it is. On the left side of the box, V equals I times R. R is V divided by I. So basically I rearranged the equation for you to solve for each individual part of it. If I multiply both sides by R, I get V on one side by itself. V is I over R. If I divide both sides by I, R is V over I. Okay? That's how you rearrange Ohm's law. Yay! There's some questions on the bottom. Ohm's law practice questions. I do believe I'd like for you to post your answers to all 5 of these as your way of me seeing if you've actually done your work. Don't write IDK. Alright. Let's see here now. This is not anywhere on the notes sheet. Get your own piece of paper out and start writing. Electric circuits. There's 2 types of circuits, parallel and series, and they can be in 2 states, open or closed. I'm going to tell you right now, open circuit is off and a closed circuit is on. Remember, electricity flows through the wire. If you open up the wire, electricity can't flow through it anymore. So open is off, closed is on. Let's talk about parallel and series for a bit. If we were in the classroom, I'd be drawing them for you, but we're not. Series circuits only have one path for the current to follow. From like the negative terminal of the battery out and around to the positive terminal of the battery, one path. Therefore, if one appliance goes out, they all go out. Appliances are things that are using the current. Voltage is different on all appliances. So the voltage in the voltage source gets distributed to all 3. It gets split up amongst them, shared out. And the more appliances you have, the less current, because each appliance puts up more resistance, and more resistance means less current. Okay. Parallel circuits have multiple paths back to the voltage source. Each appliance is on its own little path. They share some of the wires, but then there's a branch off that goes from one to the other. Therefore, if one appliance goes off, the others don't care because they still have their own electrical path. Each appliance is getting the same amount of voltage, and more appliances means more current going through the circuit. I'm not going to make you do the math on these because I have to be there to teach it to you. I don't know how to teach it to you without being in front of you. I could probably throw you on a website and you can read it fine, but I don't think that'll work for the majority of you. So I'm just going to not worry about applying the Ohm's law equation to circuit diagrams. I am going to find you a picture of circuit diagrams so you can be looking at that while I'm teaching you this last little bit here, these last 2 slides, so you can kind of have a visual of what I'm talking about. So if you have too many appliances on at once at your house, what can happen? Well, your house is done up in parallel circuits. So as each one turns on, it draws more and more current from the voltage source, the electricity going into your house. And those wires that are shared by those branches of the parallel circuit get really hot because more current flows through it. The resistance of the wire changes that current to heat, and it gets hot. So you could have the wire actually overheat, melting the insulation around it. Now you got wire on bare wood, because most of your houses, the framework is wood inside the walls. And that's a good way to get a fire. That's what people mean when they say there's an electrical fire. The wire got overheated, it got close enough to the wood, and it got hot enough for the wood to ignite. It's the word wood burning, not your wires burning. Alright, we prevent this buildup of electric current with these things called fuses and circuit breakers. Fuses have a little metal strip that melts when the circuit gets too hot, opening the circuit and killing the current. Open circuits, electricity doesn't flow, the wire cools down. Most of your modern day houses do not have fuses. There's something better called a circuit breaker. Get into that in a minute. Cars have fuses. At some point, ask your parents or whoever to find the fuse box in your car. The fuses in your car are tiny little things that plug in and pull out. You have to have specialized little tweezers to pull them out. Of course, they're just a pain to get out otherwise. And if you look inside them, they're usually clear see-through. They're color-coded, but it's still clear color, and you can see the little metal strip in there. All right. Circuit breakers have a piece of metal, let me move myself out of the way, that bends when it's heated. As that wire gets hotter and hotter, it bends, and eventually there's a switch up here, just pops a switch. Then it cools down because no more electricity going through the wire, no more heat. You got to come back and put the switch back down yourself in order to get the circuit to go back again. But turn something off first, all right? Don't leave it hot like it was. Okay, that is the end of the PowerPoints. I hope you enjoyed it. I hope the loud sounds from outside didn't distract you too much. I actually hope you didn't hear them, but if you did, sorry. And y'all have a wonderful rest of your day. Bye-bye.